Is it audible?
Yes, sir.
Just 1 minute. Okay. Hello? Yes? Yes? Yes, sir. So you can, so actually one of my student is coming and he will collect it. Yes, yes. ठीक है, ठीक है, यही वही भी अच्छा है। आप जैसे को जो वहां पे डाल दो, ऐसे ही फाइन होगा, ऐसे ही ठीक होगा। ठीक है, ठीक है, मिल जाएगा। थैंक यू, थैंक यू। Just 1 minute. Okay, let us start from where we actually ended yesterday, and we'll do something today to understand that like three group of semiconductors. Okay, so if you can remember that yesterday discussion that we had somehow finalized. Somehow we have finalized that choice of semiconductor. So since we are actually mainly targeting, so for an example, like this course would have been like a two module. Like one is actually RF, that is high frequency. Another phase would be like a high power device, power electronics, or something. But I have chosen that RF and optical because I thought like it's better things like one optic part and another part electronics. Otherwise, if it is a power electronics and RF, so it is kind of both are electronics. I mean, right? So to extreme end, I had choose because of that. Another thing, the choice of semiconductor is kind of manipulation, like not manipulation, like this whatever you are seeing, silicon, gallium arsenide, indium phosphate, germanium, gallium nitride, silicon carbide. These are the semiconductor people are mostly used. Okay? So there we don't have at the moment we don't have other choice in terms of electrical properties, even optical also. Another thing is that there are some detector people are realizing, right, other material like indium antimonite and all these things, but this is another ballgame. So you can have a compound semiconductor for detector, high sensitive detector. You can have a power electronics, power device. You can have a micro semiconductor device. You have optical devices. Lot of applications. Okay. Another thing that we have studied, we had a discussion. It is regarding that compound semiconductor based CMOS is not favorable situation. It's not that we cannot make, but it's not a favorable situation. Okay. People are confined anyhow. The gallium arsenide or compound semiconductor is costly affair, very costly affair. So silicon in that sense, it is a little bit cheap, and making CMOS out of the silicon is actually cost effective rather than spending time on that gallium arsenide indium phosphate thing. Definitely there is issue of whole dimension, like whole mobility and everything, but still, like people are not ready to put lot of efforts on CMOS based things, the CMOS based compound semiconductor. The technical aspect reason is that the whole mobility is too low, which we had a discussion yesterday. Another thing is that Even you can somehow manage it, but our demand or the consumables requirement are not that great. So that's the one of the reasons. Okay, so we had a discussion on it, and another thing that we had here, you can see we are discussing about ternary semiconductor, if you remember correctly, huh? So what we are discussing, like this part, but we have, I just informed that there is a called the ternary semiconductor, and we can form because based on your application, you can form your own semiconductor. What I mean that I am going to show you, but thing is that based on application, you can make your own semiconductor. That is not possible in silicon, but here it is possible. It's called the band gap engineering, which I'll show in a minute. Okay. So before I start, I just want to have some discussion on this in this graph. This graph is telling you have a minimum energy band gap, that is y-axis, and another one is lattice constant. This is very popular graph. It is available. It's like any compound semiconductor book. If you want to go through it, people are definitely coming this kind of graph. Very popular. What is the significance of this curve? Like suppose we are going to have a gallium arsenide based device. So does it mean that I can deposit gallium arsenide in any device, any substrate? It's not that. It's not so easy, because for an example, like look like that. So I just want to tell you, okay, suppose you have a gallium arsenide, you can see this curve. So this is actually gallium arsenide. Okay. So the first, my question is, can we deposit gallium arsenide on silicon? Silicon is here. Answer is no. So for this class, for today's class, answer is no. Why? Because gallium arsenide crystal crystal lattice constant is around 5.5. So 5.5. So it is actually 5, 1, 2, 3, 4, 5. So it is so 5.51, 2, 3, 4, no, 5, 2, 4, 6, 7, 8, 9. So 5.7, you can see. Sorry, this is actually 5.6. So you can see around 5.65, right? So this crystal structure, the lattice constant over here, it says 5.65 for gallium. What's about silicon? Silicon is around suppose 4.8 or 4. You know the 4.8. So huge silicon lattice mismatch is there. Question is whether it's good or bad. I'm not going to discuss on it. Definitely, I'll take this matter when we'll have a discussion of optical semiconductor, but like optical device. But till now, it is not good for us. That's what I told. It's for this class, for today's class, for today's 1 hour class. What I'm trying to tell is not good. Why? Because this lattice mismatch creates lot of defects. And what are the defects? Like what is the amount of defects? So you can see like 5.6 into minus 4.6 or 4.8, you can see, and divided by 4.8 into 100. So that's the amount of lattice mismatch is there. So what I'm trying to tell, like just if I try to, sorry. So what I'm trying to tell you, suppose you have something, one lattice, two lattice, three lattice, four lattice, that is actually silicon, correct? Suppose this is my silicon. And it is actually 4.8, suppose. Over and above, you want to deposit your others, that is silicon. Silicon is gallium arsenide. Gallium is a little bit large, so it would be like that. Now the question is like, what will happen this interface? So this interface, okay, that is because it is a random, because this silicon you have and you have that gallium arsenide, okay, this interface is not proper because it is a totally different lattice, so they are not sitting properly, okay. And if the lattice to lattice, atom to atom connection is not that great strong, the addition is not proper, and if the addition is not proper, it will come out easily. Like gallium arsenide will come out silicon because the interface states are, even if it doesn't come out, so what will happen? It generates lot of defects. That's the killing factor. So these are the things. So what happens sometimes that these silicon atoms try to attach these. Okay, this silicon atom try to, because this silicon, it is very confused. This is my silicon atom is very confused whether it will attach to this gallium arsenide or this gallium arsenide, right? It's kind of very unsaturated. Definitely, it's a very confusing state, and that actually generates a lot of defects over there. And that defect sometimes, yes, sometimes is so severe that you really cannot deposit gallium arsenide on silicon. So that is what I'm saying. So here, if you see carefully, like this graph tells few story. One story is that you have a huge mismatch in the gallium arsenide silicon. But again, I'm telling you whether it's a good or bad, it's not the discussion, but at the moment for this, at this class, it's bad because what you understand that if you have a huge distance, if the difference between lattice constant, your deposition of gallium arsenide on silicon is very bad. Great, fix it. Now, what else? What else would be the limiting factor for me, for us? One, okay. Similarly, you can see what else I'll tell. So similarly, you can see that gallium arsenide, whatever you think, it is a good material for germanium. So it can be deposited on germanium. That's a good thing actually. It's like, because germanium and gallium is a kind of matched lattice. Okay, so that's, remember that there are two such a match. Germanium can be here, germanium can. So there are two type of lattice structure you might have for germanium. One is sitting over here, another is sitting over here. So depends on the growth of germanium. Okay, so don't confuse on this. But it looks like the gallium arsenide can be deposited on germanium. So this curve is actually a very important for us, and this is one of the things that we have to really remember. Like, you cannot have your things randomly to any substrate. You have to go back, check different papers, different literature, and try to find out, like, if you want to deposit gallium arsenide or some other material on a particular substrate, then you have to find out that what are the crystal structure, what are the other parameters like surface roughness and all these things that will look in at the end of this course when we will have a discussion about fabrication. Okay, but this is very important. Another thing, if you are very careful, there are something called the dot 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 structure and solid structure. Like you can see this line is solid, and there is something called the dot dot dot. When it is a solid line, it means this is actually direct band gap. When it's a dot 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 line, it is means of indirect band gap. So here also we are doing same thing. You can see for an example like aluminum arsenide, we had a discussion earlier yesterday that aluminum arsenide is nothing but an indirect band gap semiconductor. While gallium arsenide is actually kind of semiconductor called direct band gap semiconductor. Now you see the aluminum arsenide is connected by a line, right? So, and not only that, it means what is the composition of this one? So if you see that gallium arsenide, aluminum arsenide is connected by a line, so my question is what is the composition of this one? The composition of this one is actually aluminum gallium arsenide. Please check it. Because gallium arsenide over here, aluminum arsenide over here. Now what I'm going to take, I'm going to discuss this phenomena little bit. Okay, so aluminum arsenide and gallium arsenide, and that I'm going to discuss this phenomena in details, what is happening over there, and then I'll come back again over. So I'll take this part. Okay. Why is my yeah. 1 minute. I just want to. I just want to share. So this one note is visible now.
Yes, sir.
Yeah. So what we are trying to discuss. So let us see. So I just copy and paste here, and I'll come back here. So what we are trying to see, trying to understand this curve, and we are trying to focus this curve. We are trying to focus this zone. Okay, carefully. So what I'm going to do? One thing is that last time when we had a discussion, last day when we had a discussion, what we are saying, gallium arsenide, it's a direct band gap semiconductor. SC for semiconductor. Okay. Now let us plot it and let us try to draw it. If you try, if I am correct, it is my gallium arsenide. Okay. So give a name, and gallium arsenide has a 4 satellite value. So this is actually satellite. So it is a direct band gap semiconductor. So it is the like what is the energy gap here? 1.42 electron volt. And if you see this part, this indirect zone, this is also 1.8 electron. Okay. So that is I'm writing Eg2. So we have to plot, now we have to plot aluminum arsenide also. So aluminum arsenide, just let me check what is the band gap, because long back I have studied, I forgot. Okay, that is actually 3.02 and 2.17. So but it is actually indirect band gap semiconductor, huh? So that means so this is Eg3 wait, what? And 2.17 this one. So this is also G4. So you understand? So this is the, let me divide it, otherwise to create some, not have any problem. Okay, so you have this part, gallium arsenide, aluminum arsenide, and this part. So in the gallium arsenide, you can see the direct band gap zone is like this part and this part. Similarly, aluminum arsenide, though it's not a direct band gap semiconductor, but direct band gap zone is this one and this one. Okay. But it's the indirect band gap semiconductor, right? But valence, conduction band lower and valence band upper is not in that same K value. And that is why it is not in the same, it's called the indirect band gap semiconductor. We know we had a discussion last semester. Now, what I'm trying to do is actually we are trying to form aluminum gallium arsenide. That's what I told, that we want to form aluminum gallium arsenide. The question is how to make gallium arsenide to aluminum gallium arsenide. It leaks like that. You already have a arsenic. Okay, only thing is that if you constantly put aluminum into the gallium arsenide, because if you add aluminum into the gallium arsenide, what will happen? Slowly. So slowly, gallium arsenide become aluminum gallium arsenide. For an example, so just try to plot one thing and that it will clear. Okay, I just want to, it's called the phase diagram. I don't know, you have done definitely what are utility point and all these things. So you have done long back, but what I'm writing here, gallium arsenide. What I'm writing here, aluminum arsenide. This is it. Okay. Here, this point where x is equal to 0, and here this point x is equal to 1. So aluminum, gallium arsenide, this is the part. So you have a x, okay, and you have a 1 minus x, right? So when x is equal to 0, okay, so you will get a gallium arsenide. When x is equal to 1, you get a aluminum arsenide, right? This is the part. So my request is that whatever I'm going to do, you try to plot in according to the scale, but which is not possible here, but it's better if you plot in according to scale. Now here, since it's a gallium arsenide and you are having two type of band gap, right? For gallium arsenide, you have a 1.42 electron volt band gap. Another one is 1.8 electron volt band gap. So let's do 1 and 2 and 3. So I'll write 1, 2 and 3. Similarly, here also 1, 2, 3. So let's present one. So this is actually, if it is 1.5, so I'll just put 1.42 over here. So that I am representing 1.42 electron volt. 1.42 electron volt, right? At this point. Okay. And that is my direct point. So you see, this is my direct point. This is my direct band gap point, correct? Okay. And what is the other band gap or other indirect band gap point? It is actually 1.8 electron volt. My audio is, am I audible? Because I am showing some.
Yes, sir.
Okay.
Yes, sir.
Okay. So here you can see there is something called the indirect band gap point, 1.8 electron volt. Okay. So let us represent 1.8 electron volt. So I'll try to represent 1.8 into the different part. No, I should have used another curve. What to be? Okay, minus. This is also 1.8 82 electron volt. Huh? So gallium arsenide. So remember, this part is my direct point. Okay. Direct point means, so this part k is equal to 0. So I'm just, k is equal to not 0, k is equal to constant. Okay, so similarly, aluminum arsenide, you see this is the only part where k is equal to constant, right? Because here my conduction band and valence band in the actually same rules. Huh? So here also I have to represent aluminum as 3.02 and 2.17. So why we make 3.02? So it is okay. So it would be little bit high. So let me represent it here. This is my 3.02 aluminum, right? Okay, and this is actually my k is equal to constant value. So I have to highlight it by this manner. Similarly, aluminum arsenide, another value is there that is called 2.17. So you can see this is my 2.17. Okay. Now what we have to do? So we have to, you understand, we have to join it. So let's take a nice car point. Yeah, I think it's there. Joined the direct point to direct point, because direct point of gallium arsenide, which we have already marked 1.42 electron volt, there the k value is constant, is try to mark in 3.02. Look, let's do it actually. Huh? Okay, another point, how you have to mark it. I don't know, maybe this one. And this is my cross section. So this we have to understand. What is happening? You just look at these two band gaps, band diagram of gallium arsenide and aluminum arsenide. When we try to merge it, what will happen? Gallium arsenide is actually a high band gap. Sorry, 1.42, and gallium arsenide is like 1.42, and aluminum arsenide direct point 3.02. When you try to merge it, when you try to mix it, when you try to diffuse it or whatever, so when you try to mix gallium arsenide to aluminum arsenide, so this one will try to increase, this one try to merge, decrease. So 3.02 will try to decrease. 3.02 means aluminum arsenide band gap try to decrease, and gallium arsenide will try to open up like that. When it would be exactly the same, so that is my particular band gap at that composition of X. Again, I'm refreshing it. So you have a gallium arsenide of 1.42. I'm talking about the direct band point, and aluminum arsenide 3.02. It's like that. When try to mix it, these two things, okay, what happen that you are actually putting lot of aluminum into gallium arsenide. What will happen? It will slowly open up. The gallium arsenide band gap slowly open up. Similarly, the aluminum arsenide thing slowly actually 3.02. So it will be slowly coming up. That's what. Okay, and how you are mixing in terms of band diagram, how you are mixing aluminum? We are mixing aluminum means your X value is increasing. X means this one. So like X value means this value. So this value is increasing, right? So when X is equal to 0, it's a pure gallium arsenide. When you increase X value like 0.1, 0.2, 0.3 means you are mixing aluminum into the gallium arsenide, and then accordingly something is happening. So that is what is happening. So second thing, what is important, which one we should look? We should look in the following manner, like band gap. So like here, if you see, gallium arsenide is this part at 3.02. That is actually the aluminum oxide. When try to open up and like that, okay. So the band gap we have to consider which is having lower energy. Means look at that. Here you see. Let me color it. You see here when you actually increasing this side, the X value. That means you are increasing aluminum in this value. What will happen? You are slowly importing aluminum over there, and this by this, so your band gap is increasing, because you see this direction is the energy direction. Your band gap is increasing, so means this is slowly your band gap is increasing, okay. But still it is direct band gap. Why it is still direct band gap? Because still my gallium arsenide is dominating. Still my gallium arsenide is dominating, and gallium arsenide is a direct band gap semiconductor. So that is why I have chosen the lower. So you can see this part 1.8 to 2.7. That is nothing but this is 1.8 electron volt of gallium arsenide. It is actually indirect portion. Similarly, 2.17, it is indirect portion. But this line, this which is joining 1.8 to 2.17, this line, it's actually indirect line. But my lowest energy state is this one. So I am considering this one because this is my lowest energy state, right? That's what I'm saying, right? So what happened when you try to mix aluminum into the gallium arsenide? Slowly, my band gap is started increasing, and that is what it is happening. Yeah. So it is slowly, it is start increasing, and it comes over there. Now you see the beautiful thing. When you touch over there, because this curve is nothing but your direct band gap part. I do understand it's a direct band gap, but suddenly after this point, this curve is not a lowest energy line. This curve is actually, because this point you can see highest energy point, right? What is the lowest energy point? This one is actually lowest energy point. Okay, let me represent it to different color. So this is my lowest energy point. And most important, this lowest energy point is nothing but a indirect zone part. Right? So that's what I'm saying. The overall curve, if you see, it looks like this one only. It goes like that. Okay, and after that, now what it means? It means, and this is the value from where this value is happening. So if you see carefully, or even if you take the literature, if it is around 0.37 value, the X value, and this value is actually 1.93 electron volt, if I am not wrong. What it means? It means, first thing, another thing which, okay, so if you try to see, okay, fine, no, let us see. Here, though I have drawn though I try to draw it is like, but this is it's not like that straight. Like it is not 2.12, it is a 1.82, and it is 2.17. So 0.17. So it is not a flat curve, huh? This is not a flat curve, which it looks like a flat curve, but it's not. It is like, it should be like that only. Huh? Just for it's due to drawing, it is not coming like my drawing. It is not coming like that, but what you are seeing, it is not flat curve. So if you see this curve, so it looks like that. If you try to increase your X value, that if you try to increase your aluminum into the gallium arsenide, the first thing what is important that you are increasing your band gap. So this is called the band gap engineering, which is very, very popular in gallium arsenide domain zone. That suppose you, for a particular device, if you want to have a particular band gap, okay, you can go for it. Like here the band gap, you see 1.4 to 2.17. So you have a tunability of band gap from 1.42 to 2.17. Anything you can choose. Okay. Definitely another, okay, I'll tell. So that means you have a choice of your own band gap material by putting aluminum into your gallium arsenide. It's a fantastic thing. Second thing, look at this part carefully. So this gallium aluminum arsenide up to X is equal to, so up to, so if you see like aluminum gallium arsenide 1 minus X X. So thing is that suppose you have a requirement that you need to have a compound semiconductor which should be higher band gap than your gallium arsenide, suppose 1.6. Okay. Not only that, that should be direct band gap. So this could be your choice. So if you have it to 1.8, so you have to find out where is 1.6. You have to find out where is my 1.6. So this is suppose my 1.6 friend. So and this corresponding to your X. So you have to put this much amount of X. You have to mix this much amount of aluminum to gallium arsenide, so that your band gap is 1.6 electron volt. Most importantly, it is a direct band gap. Suppose somebody has also come telling that I want to have the same aluminum gallium arsenide, but indirect band gap, not direct, but indirect band gap. Not only that, I want to have this band gap should be 2.2 electron, around 2.01 or 2 electron volt. That is also possible. The moment you say like that, so that means you have to identify this zone is actually indirect band gap zone. And 2.0 means this could be, okay, so somewhere here you have to, it's more or less flat. So you have to find out where would be my 2.02, and from there actually you need to put your X value. So only one thing it is important, that means it is converting your direct band gap to indirect band gap semiconductor. So the beauty is that you have a aluminum gallium arsenide, fine. You have a gallium arsenide, fine. You put aluminum over there. Based on your choice, you can transfer this gallium arsenide to direct to indirect. Number one, you can increase your band gap as well. So that is the best part of this part. Now this compound semiconductor. Now you go back here and try to see what is happening. Here what I have done, that you see what I'm trying to see this curve. So you see that this from here to here, it is a solid curve. From here to here, it is a solid curve. Over that, this is actually dot, dot, dot. And what I told you, if it is a solid curve, it is a direct band gap semiconductor. If it is a dot, 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 it is indirect band gap semiconductor. So I hope you understood this part. And see the thing is that your band gap is increasing, right? 1 to 2 point, like this part, right? So that means how you are increasing gallium arsenide to aluminum arsenide, that is a two experiment which I have not considered. I have considered just now. You are mixing the aluminum, and what is the consequence of this? The moment you try to mix the aluminum, the band gap is increasing slowly. It may be 1.8 electron volt to 2.17, but it is important. Okay. Not only that, this part it's a 0.37, X value is 0.37, and above the 0.37, your compound semiconductor, that is aluminum gallium arsenide, turns indirect band gap. Below that, it is a direct band gap. So same, this is actually beauty of this thing. Same thing is can happen. You look at this. You have a gallium arsenide. You have a gallium arsenide over here. Similarly, you have a gallium phosphate over there. Gallium phosphate is also called an indirect band gap semiconductor. And you see this curve up to here is actually, it is a gallium arsenide phosphate. Okay. Gallium arsenide phosphate here. So up to from here to here, it is like a direct band gap semiconductor. And from the dot 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 line is nothing but it is an indirect band gap semiconductor. And this junction point for gallium arsenide phosphate is a 0.4. So more than 0.4 you can have, you cannot have, like more than 0.4 you turn your gallium arsenide phosphate to indirect band gap, right? Similarly, you are having gallium arsenide and indium arsenide. This is indium arsenide and gallium arsenide. But here the thing is that both gallium arsenide and indium arsenide are actually direct band gap semiconductor. Here you will get the benefit of having band gap. So if you transfer your indium arsenide to gallium arsenide, means like if you have an indium arsenide and slowly if you mix gallium in it, your band gap will increase. Okay. So your band gap will increase, like indium arsenide is around 0.4, 0.5, 0.4 electron volt. And if you slowly increase your gallium over there, it will, you can reach up to 1.8 electron volt. Okay. Look at here, this zone. What it is telling, that at particular this X, so you are actually mixing gallium arsenide and indium arsenide. So you are actually mixing gallium into indium arsenide. At particular gallium, you will reach over here, the dot zone. And in this dot zone, you can deposit indium phosphate. Suppose you are having indium gallium arsenide. This portion is actually indium gallium arsenide, okay, of particular X, okay. At that X, you can see, if you carefully control it, you will reach at the same lattice point of indium phosphate. It means you can deposit indium phosphate of indium gallium arsenide of particular X, right? Because at this point, both indium phosphate and indium gallium arsenide of particular X value are same. So there won't be any difficulties or lattice mismatch, okay, to deposit, for depositing indium phosphate to indium gallium arsenide, okay. There are plenty of things that if you go to carb, like gallium antimonite is there, aluminum antimonite, so you can do plenty of things, okay. So most important part that this carb has generated more than 60 years, I think 50 years back, okay. And I really appreciate those people who have done this measurement. It's actually lifelong measurement. Maybe these people have spent 20 years, 10 years, 20 years to generate this data point. It's really appreciable job. Okay, it's a lifelong experiment they have done. So this curve, so now here actually what I am concluding, that you can have such a flexibility in one of having this kind of compound band gap tailoring. Not only that, transferring direct to indirect or indirect to direct. Not only that, you are actually increasing the band gap also. So while next time when somebody asks you that, okay, I want to design a particular light emitting diode, okay, at a particular wavelength, okay. So what would be my choice? For this class, for up to today's discussion, you can easily understand, no? Like for an example, like so this part, you can see it is 1.93 electron volt, this junction point. So that corresponding what lambda? Can you please tell me what is the lambda here? 1.93 electron volt. Can you tell me? Around 640. So lambda is around 640. So 640 wavelength, what is corresponding to which light? Any idea? I just type. So I think it's a green light. Let me check. Yeah, 5 for 605 it is. Okay, 642, which light? Can you tell me?
So red.
Okay, good. So that means somebody, if somebody asks you to draw, yeah, somebody asks you to draw that design LED of red, you can do. Okay, in this case, somebody asks you to design, okay, blue LED. You can also design, no? So what is blue LED? Blue LED means you have to find out what is the wavelength. You know what is the wavelength? Maybe 500 nanometer. I'm not so sure. I'm just find out. Now at the 500 nanometer corresponding what energy is required, that you find out, right? So suppose 500 nanometer, what is the energy, that also you can find out. And to get that energy, find out, first of all, it is, since it is a LED, you need to have a direct band gap. Okay. Now you know 500 nanometer corresponding what energy. So you find out what is the energy that you are looking for it. Suppose this is the energy you are looking for it. Okay. And then you just drop it over there. Find out what is the X value. Find out what is the X value. That X value, that means that aluminum concentration you have to mix into your gallium arsenide, and you will get that LED. Okay. So that is the beauty of this tailoring of this compound semiconductor. Okay. So please remember, I think, okay. There are a lot of other variation is also there. As I told you, indium gallium arsenide, gallium phosphate, all these things. So please try to do all these things. Okay. Whenever you have a time, if you have a time, so please try to compute it at least one or two more to get more idea that how people are changing that structure and everything. So I'm stopping over here. I'm not going because I have another meeting of around 1:45. Okay. So our next meeting on Monday, and we'll start 9 o'clock, 9 to 10 and 10 to 11. But there is one issue. Next Monday, I think our ISRO chairman is coming, and it looks like that I have to be there in that ISRO chairman some activity. So it is not been finalized. So if something actually is not possible, so I'll drop a message to the group. Okay. Similarly, Apurva also I'll drop a message. So if I can take, I'll take. If I cannot take, I'll inform you. Okay. So, tell me. Yes.
Sir,
Yes.
any prerequisites for this course, or like any reference book should I refer?
Uh, there is no prerequisite. What thing is that what I always refer that every student should have a basic knowledge of fundamental of semiconductor device. Okay, I think
Okay, sir.
all have that part, no? Like,
Yes, sir. Yes, sir.
yeah. So only
The, I'm not somewhere. I'm not getting the link, so that's why I thought like if I
okay.
read some
What are the things that you are not getting the link?
maybe I will see previous lectures and I can relate to that. I think this is the second lecture. That's why I'm not like.
Okay. Okay, so you check it and you check your friends also that our semiconductor, I mean like VLSI friends, your friends, you can discuss. Okay. Okay, so till now I have not discussed anything physics, that I'm sure, which I'm going to discuss next day. Next day we are starting Schottky junction, Schottky diode. Okay, that time we'll do the dirty work like all the derivation and everything. Okay, till
Okay.
I have not done anything great physics. No, I just took a very simple thing. Only thing is I had I have considered you have a good knowledge of direct and indirect band gap semiconductor, correct?
Yes, sir. Yes, sir.
Apart from that, nothing I have taken.
Okay.
And books actually, unfortunately, there is one books are available that is actually, I don't know what to say. That is actually VLSI fabrication principle. Okay, silicon and gallium arsenide. That is Saurabh Gandhi. That I will refer. And there is no as such great physics. Means I mean to say like physics are same. What I am trying to impose on gallium arsenide. So you understand there is no standard books available. But that is the bad part in compound semiconductor. Okay. But still I have some collection of papers. But I think our first year students are not here at IST. So I cannot share because that is the hard copy I have. Uh, Only optical part you can take help of Pallav Bhattacharya. But here for electrical part, I think Streetman Banerjee or SMG is fine. Absolutely fine. That you realize. Because I want to build the story on your existing knowledge. Only thing is that since you already have a good knowledge on silicon, so whenever there is a change of some other things will come like a compound semiconductor that you can actually put it over there. Okay. Other than that, there is no fundamental change of the theory. Theory is same, so we cannot do anything else. Okay. But unfortunately, there is no as such great books available for compound semiconductor for this course. The course is designed totally different in advanced mode, which is not available. It is very, very advanced course.
Okay, sir. Okay.
Okay. But I believe that if you follow it, there should not be any problem.
Yes, sir. Yes, sir. Like this is my second class, so
Yeah. Fine. No issue. Okay, so I have a meeting, so I'm leaving now. Thank you. Anything else?
No, sir.
Thank you.